In probability, we know the definition of classical probability or axiomatic approach, or the basic definition as introduced by Kolmogorov, which is based on a particular sigma field, and hence we derive the probability space. Now, one thing that we have already encountered in many situations, like if we have been given a particular event and we are interested to see what happens to the probability of another event when that first event has already occurred. We all know that this is known as conditional probability. Now, today we are going to discuss this conditional probability in great detail, more specifically the mathematical or statistical basis of conditional probability. That means, we will derive or we will develop a particular probability space, or we will see how from the given probability space we can actually define a conditional probability. And naturally, when we define conditional probability, obviously we can think about the conditional expectation, and it is interesting to see that today we will first try to develop conditional expectation, and from there we will go into the concept of conditional probability or concept of conditional probability measure. So, today we will introduce formal definition of conditional expectation or conditional probability as well as conditional probability measure from a very theoretical point of view. So, the objectives can be summarized as: I would like to introduce the concept of conditional expectation and see whether we can formally define conditional expectation from a given probability space. Now, usually contrary to the other approach, here I will first define conditional expectation, and then I will move on to defining conditional probability as well as conditional probability measure. Now, I emphasize on the term probability measure because we will see that the way we define conditional probability measure is actually constitutes one particular measure or probability measure within some space. So, let us first give an idea of what is the meaning of this conditioning or conditional probability. The conditioning simply means that we are going to use some auxiliary information. Now, why we should use auxiliary information? Now, if for some reason some information is available and that is related to the event of our study or our interest, we can use that extra information. So, conditioning probability incorporates this information which we might call additional knowledge to change the unconditional probability, because if we incorporate or induce this auxiliary information, naturally the probability of the unconditional probability of a particular event should change, is expected to change. So, this is the important part of studying this conditional probability. So, conditional probability basically incorporates this additional information, and that will ultimately affect the unconditional probability of that particular event of interest. So, we can think of this imposing this additional information or conditioning on a particular event imposes some restriction through the conditioning event, because that is quite natural, because it actually changes the probability of or unconditional probability of that particular event. So, the idea is that conditioning basically gives us more information or prior information, and how to incorporate that prior information into the probability of a particular event. So, let us formally define, let us start defining this formally, this conditional expectation or conditional probability. So, let us start with a particular probability space which we call omega script f and p. P is the probability measure defined on this measurable space, and also define a script a, which is a sub sigma field of the basic sigma field f. Now, naturally, since this is a probability space, script f is the sigma field generated by the class of subsets of omega. So, script a we assume that is a sub sigma field of the basic sigma field script f. Now, we can define a function which is script f measurable, and we call this function as x. So, let x be a measurable function of omega whose integral exists. that is modulus of expectation of x less than equals to infinity, and script A is a subset of script f. Then we can write phi of b equals to integral over b x dp, where b belongs to script A, and script A is a sub sigma field. So this phi b is a restriction of phi to sets of script A, and we denote this by phi given script A or phi conditioned on script A. So here comes the additional information through script A. Now it is easy to see that this phi is script A measurable, and phi is absolutely continuous with respect to the probability measure. That is this is the original measure that under which we are working. Or in other words, we can say that since phi is absolutely continuous with respect to b, we can it is also sometimes it is also denoted by, or we sometimes say that phi is p continuous. These two are exactly same thing. And also phi is sigma additive function. So these are a few properties which are immediately obvious with respect to phi function. Now, since these three conditions are satisfied, then naturally we can apply Radon-Nikodym theorem to show that there exists an script A measurable function y, which is ddp of phi on omega. Now this y equals to d phi dp is called the conditional expectation of x given script A, and this is denoted by E of x given script A. So this is the formal definition of conditional expectation of a random variable of x, in this case given a sub sigma field script A, or given a particular event which belongs to the script A, which we will show in a minute. Now y basically is defined by two conditions. First condition is that y must be a measurable, script A measurable, and the second condition, if we consider integral of y dp over b, which is same as integral over b of x dp. Now we can write this as integral over b of d phi given A with respect to dp into dp, and this is true for all b belongs to script A. So this y is defined by these two conditions. Now let us look at a few facts with respect to this conditional expectation. So first assume that x is an script f measurable function which is integrable. That means modulus of expectation of x less than equals to infinity, and yt is a family of random variables where t belongs to some set capital T, is a non-empty families of random variables, and script A suffix t, script A t, where t belongs to capital T, is a family of sigma fields of sets in this case. Now we usually define expectation of x given yt where t belongs to capital T. That means we are trying to evaluate the expectation of x when capital Yt has occurred. Now t belongs to capital T, so this is a non-empty, and we assume that this is a non-empty family of random variables. Now this thing we usually write as expectation of x given sigma yt, that means sigma field generated by the set of random variables yt, where t belongs to capital T. So these two are exactly same. That is the way we define. Similarly, exactly similarly, we can define expectation of x given script at, where t belongs to capital T, equals to expectation of x given sigma field generated by this sigma fields, that is script at, where t belongs to capital T. That means whenever we say that expectation of random variable given another random variable, that means this given random variable means we usually mean that this is nothing but the sigma field generated by that random variable. So in particular, if we write expectation of x given y1, y2, yn, more than one variable we can think of, which is nothing but expectation of x given sigma field generated by y1, y2, yn. So naturally, as I have just mentioned, that expectation of x given y is nothing but expectation of x given sigma y, that means sigma field generated by y. So this is the way we usually define, and this is the notations that we will use interchangeably for the rest of this talk and later also. Now, if we carefully look at the formulation or this definition, we see that expectation of x given capital Y1, Y2, Yn, this should be a function of Y1, Y2, Yn, but conditioning on Y1, Y2, Yn, so naturally this entire quantity should belong to sigma field generated by Y1, Y2, Yn, or in other words we can say that this is sigma Y1, Y2, Yn measurable. So there must exist a Borel measurable function. So we call this, whenever I say that expectation of x given Y1, Y2, Yn, we can think of this function as a Borel measurable function g on Rn. That means mathematically we can write that expectation of x given Y1, Y2, Yn is nothing but expectation of x given sigma field generated by Y1, Y2, Yn, which is nothing but a Borel measurable function g of Y1, Y2, Yn. Or conversely, we can think that if g is a Borel measurable function on Rn such that modulus of expectation of g Y1, Y2, Yn less than equals to infinity, that means it is integrable, then for every b belongs to sigma field generated by Y1, Y2, Yn, we can write integral over b of g Y1, Y2, Yn dp is nothing but integral of b over b of x with respect to p, that is integral over b x dp. Then if this thing holds, then we can immediately see that g of Y1, Y2, Yn is nothing but expectation of x given Y1, Y2, Yn almost surely. So this holds for almost surely or almost everywhere. Now in a particular situation, let us assume that y is nothing but the indicator function for a set B, for some set B that belongs to script f. Script f is the original sigma field in the original probability space. So if y equals to IB, for some B belongs to script f, then naturally sigma field generated by y contains only 4 sets, that is phi, there is an empty set, B, B complement and omega. And for every version of expectation of x given y must be constant on each of the events B, B complement, implying that expectation of x given y of omega equals to 1 by probability of B integral over B x dp if omega belongs to B, and if omega belongs to B complement, this will be 1 by probability of B complement integral over B complement x dp. It is clear that where either of the constants on the right hand side can be taken as any number in extended real line, that is r bar, when the corresponding event B or B complement has 0 probability. So this is the way we define, and this actually fits into the formal definition of conditional expectation. Now once we define conditional expectation, then one can ask the question that is it, since we know that initially we have defined probability and from there we have defined random variables and hence expectation. So here for the sake of simplicity we have defined, we move the other way around, that is we have defined conditional expectation first. So naturally we should be able to define conditional probability from now on. So assume that there are 2 sets A and B that belongs to script f and another script A which is a sub sigma field which is a subset of script f. Then define probability of A given script A equals to expectation of indicator function of A given script A. This part is pretty obvious because expectation of indicator function of a set is nothing but the probability of that set, and probability of A given B we define as expectation of IA given IB. Then if we define this way, then probability of A given script A is called the conditional probability of the event A given the sub sigma field script A, and naturally this is a script A measurable function of omega which satisfies integral over C probability of capital A given script A dp equals to integral over c ic dp for c belongs to script A. So, this is the way we define conditional probability, and probability A given B is called the conditional probability of the event A given B. Therefore, if probability of B greater than 0, from the previous slide we can immediately write probability of A given B equals to 1 by probability of B into integral over B of IA dp, because this we have defined in terms of expectation of indicator functions, which is equals to probability of A intersection B by probability of B. So, now we have seen that this is the definition that we know about the conditional probability, but this comes from, so this we need some mathematical sophistication to come to this definition. So, once we define conditional probability, natural question would be, can we define a probability measure, that is a conditional probability measure, from this conditional probability? Then answer is definitely yes. If mu of omega is non-zero and finite, we can view mu of any set, mu function with respect to of any set divided by mu omega as a generalization of probability measure, because this measure this function takes the maximum value 1, because mu of omega is finite. So, naturally this can be treated as a generalization of probability measure. Let B be any arbitrary but fixed subset of omega, and B belongs to script f. Then consider the following class of events. B intersection script f equals to B intersection A, or the set of sets which is of the form B intersection A such that A belongs to script f, and we call this class of events as script fb. Then this class is a sigma field of subsets of B. So, naturally it is clear that we can immediately say that since this is a sigma field, we can immediately say that B and script fb is a measurable space. Now, once we have a measurable space, then only we can define a probability measure. So, now we got a probability space. So, by probability measure defined in this, the only problem is that probability measure defined on this space is not normal, because probability of B may not always be unity. But it is not a very difficult thing to make it normal. So, just define a probability measure as probability P suffix B of B intersection A equals to probability of B intersection A by probability of B on script fb on this sigma field, provided probability of B greater than 0. Now, with this definition of probability, with this definition of probability function, we can immediately say that B script fb and Pb is a probability space, and this Pb is called the conditional probability measure, because this is the function, probability function of the measured function. So, we can call this as conditional probability measure given B. Now, we denote this measure by Pb, or P of some set dot given B. So, this is the way we define conditional probability measure. The only important thing is that although it is very easy, that probability of B may not be equal to 1 always. So, we just divide this, we just normalize it using dividing the any event, probability of any intersection of two events divided by probability of B. So, it is a very easy way to define or to construct a conditional probability measure. So, this gives us a formal definition of a probability space on which we can define conditional probability measure. Now, there are a couple of things. Since we say that this is a probability measure, we should check three important properties of a measure, or rather probability measure. First one is Pb is non-negative, which is obvious from the definition, and Pb of omega is 1, which is again obvious, because we have normalized this Pb, we have defined Pb measure by normalizing by probability of B, or that means dividing by probability of B. And a little bit of mathematics, very simple mathematics, will ensure that Pb is sigma additive on script f. That means, it ensures that this is a probability measure. Now, everything is coming from omega f. So, this is Pb is a probability measure on omega f. Because naturally, since this is a probability measure of omega a on omega script f, we can immediately say that omega script f Pb is also a probability space, and this Pb of a is called conditional probability of a given b, and Pb of any set is called dot, which is denoted by dot, is called conditional probability distribution on omega script f, because whenever we have probability of a number of sets on a particular measurable space, we can easily define the probability distribution on that space, and since we are dealing with conditional probability in this case, we can easily define conditional probability distribution. So today we have seen how to develop the concept of conditional expectation, conditional probability and conditional probability measure from a given probability space or based on a particular probability space with which we already are acquainted with. So, this gives a very theoretical basis of this concept of conditional expectation and conditional probability, and we have seen that our earlier notion of conditional probability clearly fits into this new, not really new, but this formal theoretical representation of conditional probability and expectation. So, in the next talk we will extend this idea and we will discuss some more theorems relating to this conditional expectation.